Welcome to the series of e-learning modules on Pert. By the end of this session, you will be able to explain the importance of using Pert, explain the Pert network techniques. Let us start with an introduction. Complex projects require a series of activities, some of which must be performed sequentially and others that can be performed parallel with other activities. The collection of series and parallel tasks can be modeled as a network. The program evaluation and review technique is a network model that allows randomness in activity completion time. The program or project evaluation and review technique, commonly abbreviated as PERT. PERT is a statistical tool used in project management which is designed to analyze and represent the tasks involved in completing a given project. It was first developed by the United States Navy in the 1950s. It is commonly used in conjunction with the critical path method. The Navy Special Projects Office, charged with developing the Polaris submarine weapon system and the fleet ballistic missile capability, has developed a statistical technique for measuring and forecasting progress in research and development programs. The program evaluation and review technique, codenamed PERT, is applied as a decision-making tool designed to save time in achieving end objectives and is of particular interest to those engaged in research and development programs for which time is a critical factor. The new technique takes recognition of three factors that influence successful achievement of research and development program objectives, that is time, resources, and technical performance specifications. PERT employs time as the variable that reflects planned resource applications and performance specifications. With units of time as a common denominator, PERT quantifies knowledge about the uncertainties involved in developmental programs requiring effort at the edge of or beyond current knowledge of the subject, effort for which little or no previous experience exists. The technique is a management control tool that sizes up the outlook for meeting objectives on time, highlights danger signals requiring management decisions, reveals and defines both criticalness and slack in the flow plan or the network of sequential activities that must be performed to meet objectives, compares current expectations with scheduled completion dates and computes the probability for meeting scheduled dates, and also simulates the effects of options for decision before decision. PERT is a method to analyze the involved tasks in completing a given project, especially the time needed to complete each task and to identify the minimum time needed to complete the total project. It is more of an event-oriented technique rather than start and completion oriented and is used more in projects where time is the major factor rather than cost. It is applied to very large-scale, one-time, complex, non-routine infrastructure and research and development projects. This project model was the first of its kind, a revival for scientific management founded by Frederick Taylor, Taylorism, and later refined by Henry Ford, termed Fordism. DuPont's critical path method was invented at roughly the same time as PERT. Now coming to Pert terminologies. Let us now discuss about various Pert terminologies. Pert event, a point that marks the start or completion of one or more activities. It consumes no time and uses no resources. When it marks the completion of one or more tasks, it does not reach, that is, does not occur until all of the activities leading to that event have been completed. Predecessor event. An event that immediately precedes some other event without any other events intervening. An event can have multiple predecessor events and can be the predecessor of multiple events. Successor event. An event that immediately follows some other event without any other intervening events. An event can have multiple successor events and can be the successor of multiple events. Pert activity. The actual performance of a task which consumes time and requires resources such as labor, materials, space, machinery. It can be understood as representing the time, effort and resources required to move from one event to another. A Pert activity cannot be performed until the predecessor event has occurred. Next is the optimistic time, denoted by O. The minimum possible time required to accomplish a task, assuming everything proceeds better than is normally expected. Pessimistic time, denoted by P. The maximum possible time required to accomplish a task, assuming everything goes wrong but excluding major catastrophes. Most likely time, denoted by M. The best estimate of the time required to accomplish a task, assuming everything proceeds as normal. Next is the expected time, denoted by TE. The best estimate of the time required to accomplish a task, accounting for the fact that things don't always proceed as normal, that is, the implication being that the expected time is the average time the task would require if the task were repeated on a number of occasions over an extended period of time. TE is equal to 0 plus 4m plus P divided by 6. Next is the float or slack. It is a measure of the excess time and resources available to complete a task. It is the amount of time that a project task can be delayed without causing a delay in any subsequent tasks, that is free float, or the whole project, that is total float. Positive slack would indicate ahead of schedule, negative slack would indicate behind schedule, and zero slack would indicate on schedule. Next is the critical path. The longest possible continuous pathway taken from the initial event to the terminal event. It determines the total calendar time required for the project, and therefore any time delays along the critical path will delay the reaching of the terminal event by at least the same amount. Next is critical activity. An activity that has total float equal to 0. An activity with zero float is not necessarily on the critical path, since its path may not be the longest. Lead time. The time by which a predecessor event must be completed in order to allow sufficient time for the activities that must elapse before a specific Pert event reaches completion. Lag time. The earliest time by which a successor event can follow a specific Pert event. Fast tracking. Performing more critical activities in parallel. Next is the crashing critical path, which is the shortening duration of critical activities. Now moving on to Pert implementation. What is implementation? The first step to scheduling the project is to determine the tasks that the project requires and the order in which they must be completed. The order may be easy to record for some tasks, such as when building a house, the land must be graded before the foundation can be laid, while difficult for others when there are two areas that need to be graded, but there are only enough bulldozers to do one. Additionally, the time estimates usually reflect the normal non-rush time. Many times, the time required to execute the task can be reduced for an additional cost or a reduction in the quality. Following are the steps in the PERT planning process. PERT planning involves the following steps. First is to identify the specific activities and milestones. Second, to determine the proper sequence of the activities. Third, to construct a network diagram. Fourth, to estimate the time required for each activity. Fifth, to determine the critical path. And sixth is to update the PERT chart as the project progresses. Let us understand the steps on detail. Identifying activities and milestones. The activities are the tasks required for completion of the project, and the milestones are the events marking beginning and end of one or more activities. It is helpful to list the task in a table that in later steps can be expanded to include information on sequence and duration. Determine activity sequence. This step may be combined with the activity identification step since the activity sequence is evident for some tasks. Other tasks may require more analysis to determine the exact order in which they must be performed. Construct the network diagram. Using the activity sequence information, a network diagram can be drawn showing the sequence of the serial and parallel activities. For original activity, on arc model, the activities are depicted by arrowed lines and milestones are depicted by bubbles or circles. If done manually, several drafts may be required to correctly portray the relationships among activities. Software packages simplify this step by automatically converting tabular activity information into a network diagram. Estimate activity times. Weeks are commonly used unit of time for activity completion, but any consistent unit of time can be used. A distinguishing feature of PERT is its ability to deal with uncertainty in activity completion of times. For each activity, the model generally includes 3 time estimates: optimistic time, most likely time, and pessimistic time. The expected time may be displayed on the network diagram. Determine the critical path. The critical path is determined by adding the times for the activities in each sequence and determine the longest path in the project. The critical path determines the total calendar time required for the project. If the activities outside the critical path speed up or slow down, the total project time does not change. The amount of time that a non-critical path activity can be delayed without delaying the project time is called a slack time. If the critical path is not immediately obvious, it may be helpful to determine the following 4 quantities for each activity. ES is the earliest start time, EF is the earliest finish time, LS is the latest start time, and LF is the latest finish time. These times are calculated using the expected time for the relevant activities. The earliest start and finish times of each activity are determined by working forward through the network and determining the earliest time at which an activity can start and finish considering its predecessor activities. The latest start and finish times are the latest time an activity can start and finish without delaying the project time. They are found by working backwards through the network diagram. The difference between the earliest and the latest time of each activity is the activity's slack. The critical path then is the path through the network in which none of the activities have slack. Since the critical path determines the completion date of the project can be accelerated by adding the resources to decrease the time for the activities in the critical path. Such a shortening of the project sometimes is referred to as project crashing. Update as project progresses. Make adjustments on the PERT chart as the project progresses. As the project unfolds, the estimated times can be replaced with actual times. In cases where there are delays, additional resources may be needed to stay on schedule and the Pert chart may be modified to reflect the new situation. Following are the advantages. Pert chart explicitly defines and makes visible dependencies, that is precedence relationships between the work breakdown structure, commonly WBS elements. Pert facilitates identification of the critical path and makes this visible. Pert facilitates identification of early start, late start and slack for each activity. Pert provides for potentially reduced project duration due to better understanding of dependencies, leading to improved overlapping of activities and tasks where feasible. The large amount of project data can be organized and presented in diagram for use in decision making. Now following are the disadvantages. There can be potentially hundreds or thousands of activities and individual dependency relationships. Pert is not easily scalable for smaller projects. The network charts tend to be large and unwieldy, requiring several pages to print and requiring special size paper. The lack of a time frame on most Pert or CPM charts makes it harder to show status, although colors can help. For example, specific color for completed nodes. When the Pert or CPM charts become unwieldy, they are no longer used to manage the project. Now coming to Pert chart. What it is. A Pert chart is a graphic representation of a project schedule showing the sequence of tasks, which tasks can be performed simultaneously, and the critical path of tasks that must be completed on time in order for the project to meet its completion deadline. The chart can be constructed with a variety of attributes such as earliest and latest start dates for each task, earliest and latest finish dates for each task, and slack time between tasks. A Pert chart can document an entire project or a key phase of a project. The chart allows a team to avoid unrealistic timetables and schedule expectations to help identify and shorten tasks that are bottlenecks and to focus attention on most critical tasks. When to use it? Because it is primarily a project management tool, a Pert chart is most useful for planning and tracking entire projects or for scheduling and tracking the implementation phase of a planning or improvement effort. How to use it? Identify all tasks or project components. Make sure the team includes people with first-hand knowledge of the project so that during the brainstorming session, all component tasks needed to complete the project are captured. Document the tasks on small note cards. Identify the first task that must be completed. Place the appropriate card at the extreme left at the working surface. Identify any other tasks that can be started simultaneously with task 1. Align these tasks either above or below task 1 on the working surface. Identify the next task that must be completed. Select a task that must wait to begin until task 1 or a task that starts simultaneously with task 1 is completed. Place the appropriate card to the right of the card showing the preceding task. Identify any other tasks that can be started simultaneously with task 2. Align these tasks either above or below task 2 on the working surface. Continue this process until all component tasks are sequenced. Identify task durations. Using the knowledge of team members, reach a consensus on the most likely amount of time each task will require for completion. Duration time is usually considered to be elapsed time for the task rather than actual number of hours per day spent during work. Document this duration time on the appropriate task cards. Construct the Pert chart. Number each task, draw connecting arrows and add task characteristics such as duration, anticipated start date and anticipated end date. Determine the critical path. The project's critical path includes those tasks that must be started or completed on time to avoid delays to the total project. Critical paths are typically displayed in red. Now let us have an example. Considering an example on Pert chart. The construction of a cottage requires the performance of certain tasks. The following table 1 lists the various tasks with their priority relationship. In the table, first column indicates the code of task, second column indicates the task to be performed, third column indicates the duration in weeks, and fourth column represents the prerequisites task. The start task, that is A, and finish task, that is W, are added. A is linked to task A and W is linked to task K. Let S be the set of all tasks and consider the partial order relation R defined on S as follows. For all tasks X and Y in S, X R Y implies X is equal to Y or X precedes Y. The minimum time required to finish this job is calculated using project evaluation and review technique. The Pert diagram of the project is shown in the figure. In this representation, the tasks are the vertices of the graph. The length of each task is the duration of the corresponding task. The start and finish of a task are two stages of the project. We can define an initial stage as start and a final stage as finish and a certain number of intermediate stages. Each stage is defined by tasks already carried out. In the beginning milestone of the project is start stage. The start followed by task A, which is carried out in 7 weeks. After finishing stage A, we have two options. We can start task B and task D simultaneously. Task B takes 3 weeks to finish and task D takes 8 weeks to finish the job. Task B is immediately followed by task C, which takes 1 week to carry out. The minimum time required to start task C is the total time required to finish task B and A, which is 10 weeks. Task C is followed by task E. To start task E, we have to finish C and D. C is finished in 11 weeks and D is finished in 15 weeks. So it is very common that we cannot start task E before finishing task D, which takes 15 weeks to carry out. The same way we can decide the earliest time to start each task, which is shown in the table below. The above analysis shows that at least 21 weeks is required to complete the project. The minimum duration of the project will be the length of the longest path between the initial stage and the final stage. This is shown in with the darker line in the figure. If we delay any work in this path, we delay in the project finish time. That means delay in performing any of these tasks in the path cause delay in the time required to finish the project, and for these reasons this path is known as critical path. The tasks outside the critical path can be delayed by certain amount of time. For example, task E is not on critical path and it is followed by task K. If we delay E by 3 weeks, then its earliest start time, then we can start the task K as per its earliest start time, because K must be started after finishing J, which takes 20 weeks. We can finish task E in 20 weeks by delaying 3 weeks. In the opposition, if we delay work on the critical path, we delay the time to complete the project. For example, 3 weeks delay in task J caused 3 weeks delay to start K, and K starts after 3 weeks than its earliest start time, and these caused 3-week delay to complete the project. Now if we finish task J earlier by 1 week, then we can also reach task K earlier by 1 week and finish it off. And finally, the overall project is also finished 1 week before. Now coming to the summary. Here's a summary of our learning in this session, where we have understood the importance of using PERT, the PERT network techniques. Thank you.